Open your freezer. Inside, there's ice. Frozen vegetables, maybe a rock-hard pizza, and then there's ice cream. It's frozen, but not solid. You can scoop it. You can bite it. And somehow it melts smoothly on your tongue. That shouldn't be possible. Ice cream is mostly water. And frozen water is supposed to turn into hard, unforgiving ice. So why doesn't ice cream? Why isn't it a solid block that needs a knife instead of a spoon? The answer is more interesting than it looks, because ice cream doesn't just freeze. It outsmarts freezing. Let's start with what freezing normally does. When water gets cold enough, its molecules slow down. As they lose energy, they snap into a tight, repeating pattern. That pattern is ice. Once that structure forms, the result is stiff, solid, and strong. That's why ice cubes are hard. That's why frozen lakes can hold cars. That's why plain water in your freezer becomes impossible to scoop. If ice cream followed this rule, it would be useless as a dessert. But ice cream never lets water fully take control. Here's the first big secret. Ice cream is not a single solid. It's a mixture of many things frozen together at the same time. Inside ice cream, there are tiny ice crystals, a thick liquid made of sugar and water, fat from milk or cream, and thousands of microscopic air bubbles. This makes ice cream closer to a frozen foam than a block of ice. Those air bubbles matter more than you think. Air breaks up the frozen structure, creating weak points that stop ice from forming one solid mass. Instead of one giant sheet of ice, you get millions of tiny frozen regions separated by air and fat. That alone makes ice cream softer. Now let's talk about sugar, the biggest rule breaker in the recipe. Sugar doesn't just add flavor. It actively interferes with freezing. When sugar dissolves in water, it gets in the way of water molecules lining up neatly. The water wants to freeze. The sugar keeps interrupting. So instead of freezing at the normal temperature, the mixture freezes more slowly and unevenly. That means something strange happens in your freezer. Some of the water turns into ice, but some of it never freezes at all. Even at freezer temperatures, part of ice cream stays liquid. That liquid acts like a built-in softener, stopping the whole thing from turning rigid. Take away the sugar, and ice cream loses this protection. What you're left with is frozen milk, hard, grainy, and unpleasant. But sugar alone isn't enough. Texture matters just as much as temperature. Ice cream lives or dies by the size of its ice crystals. Large ice crystals feel rough and crunchy. They scrape your tongue. They make ice cream taste cheap or old. Small ice crystals feel smooth and creamy. Your tongue can't even detect them. That's why ice cream is frozen quickly and stirred constantly while it freezes. Fast freezing creates many tiny crystals instead of a few large ones. Stirring prevents crystals from growing bigger. This is also why refrozen ice cream tastes terrible. When ice cream melts and freezes again, crystals grow larger. The damage is permanent. The temperature didn't ruin it. Time did. Now let's talk about fat, the ingredient that makes ice cream feel indulgent. Fat behaves very differently from water when it freezes. Water becomes rigid. Fat stays soft. As ice cream freezes, fat droplets partially stick together, forming a loose network throughout the dessert. That network holds air in place, slows down melting, softens the overall structure. Fat also coats your mouth, reducing how cold ice feels on your tongue. That's why low-fat ice cream often feels harder, colder, and icier, even when it's the same temperature. Fat doesn't just add richness, it adds control. Air is the next hidden ingredient. Ice cream is whipped as it freezes, trapping air inside. This air makes ice cream lighter and easier to scoop. It also acts like insulation, slowing heat transfer. From a physical point of view, air prevents ice from becoming continuous. Instead of one solid frozen mass, ice cream becomes a collection of tiny frozen pockets surrounded by softer material. More air means softer ice cream. Less air means denser, richer ice cream. That's why premium ice cream feels heavier in the spoon. Now think about how ice cream melts. Ice melts quietly. It slowly turns into water. Ice cream doesn't melt, it collapses. As it warms, fat begins to melt, air escapes. Ice crystals dissolve into the liquid around them. The structure falls apart from the inside. That's not an accident. Ice cream is designed to melt quickly in your mouth, but slowly in a bowl. It's engineered to fail at just the right speed. Every part of ice cream is carefully balanced. Too much water and it freezes solid. Too little sugar and it becomes brittle. Too little fat and it feels sharp and cold. Too much air and it feels empty. Even tiny ingredients help control texture and stability. Ice cream isn't simple food. It's controlled chaos, frozen just enough to hold its shape, but never enough to become ice. So does ice cream really break the rules of freezing? Not exactly. It follows the rules, but it uses them against each other. By mixing water with sugar, fat, and air, ice cream stays frozen without ever becoming solid. The next time you scoop ice cream from your freezer, remember, you're not holding frozen water. You're holding a carefully engineered illusion, one designed to defeat ice itself. And that's why ice cream works. Thank you for watching. And if you'd like more videos like this, subscribe to the channel for more simple explanations of how the world around you really works.